let's get started. And we're kind of stopped here. Okay, that's where we kind of stopped. So we said we have this protocol, PBFT, and it goes through these phases. Client send a message, then the primary proposes that message to everyone. Then we have a prepare phase, and then we have a commit phase, and then we have an inform phase that informs the client. And once a replica receives a message from the primary, it sends a prepare message, including the primary's message inside its prepare message. And once it acquires that message from the core, meaning it can form a 12+1 majority, then it enters the client. That particular replica enters the prepare state or a locked state. And then at that point, it sends a commit message. Again, we have another exchange of messages. And at this point, once it collects enough commit messages, meaning it can form a commit core, then it enters a committed state. Once it enters the committed state, then it forms the client. At least from the perspective of that replica, the transaction is committed. Okay. So again, that was just a quick reminder of the basics of this protocol. So we have two phases of quadratic communications. And now the question is, we're kind of stopped last time, is that once we arrive at this state, this prepare state, and your question was, so let's hear your question again.
What is the provision? What is it?
Yeah, so what is the prepare? So anybody else had a chance to think about, so what do we accomplish, or why do we need this phase? Yes.
The command.
The transaction or the command that it received. Okay, so what's the purpose of it? So what's the use of that? So we say it. So you're a replica, I'm the primary, I send you a transaction, and you say you got to tell everybody else. Why? What will you accomplish by doing that? Be precise, be exact. What would you accomplish by telling everybody? What is real?
That you're not malicious.
So if you send a message to everybody, why is that you're not malicious? Again, we talked about this last time. Malicious doesn't mean that it doesn't send a message. Malicious doesn't mean that it always has to behave badly. Malicious also means, if it's a clever one, it's trying to remain undetected. Okay, so that's important. Did everybody hear that? Okay, so repeat it. Okay, so primary, so then how does this solve it? Or how does it then address that? So good replica will receive the same thing. So then what do? I send you a message, you tell everybody what I sent you. I send you a message, you also tell everybody what I sent you. I send you, you tell everybody. And now, what messages do you receive? And then what can you infer from that or conclude from that?
Which one is the actual message?
What do you mean by actual message? No, simpler than that. A lot simpler than that. What can you detect? Not what they do. Simpler than that. Majority what? What's a bigger majority compared to majority? What can you detect? No. What was the reason everybody was sending it? Yes?
That everyone see the same thing.
Make sure everyone received the same thing. Make sure the primary didn't lie. So make sure that I send the same message to you and to you and to you and to you and to you. Because maybe how do you know if I did that or not? But if you do a round of exchange, then you all see what messages I had sent. So if I had tried to equivocate or had tried to lie and I had to try send a different message to this side and different message on that side, through this exchange of messages, you will see, wait a minute, that's not the case. Yes. So wrong is, it's not about wrong. The message the primary sent, it's an actual client message. So that message, I mean, of course, the primary can just send random stuff. I mean, that's detectable and that's not really, it's really, I mean, you know, if the primary sends just a garbage message or a random message, replica won't even prepare it. If I see a random message that doesn't have any authenticity, I'll just drop it. I wouldn't even engage in to prepare. So, but it's possible that there are multiple clients and I have multiple valid transaction. I send one valid transaction to this side and I send a different valid transaction to this side of it. So now I could send different transaction, different valid transaction. So each replica will look at the transaction they received. They validate it. Okay, looks good. It's a valid transaction. But at this point, R4 doesn't know whether R3 had got the same transaction or not. It just knows that primary had told him, here's your transaction. But R3 got, maybe she got different message. You don't know what R3 has got. But if now I share the message that I got from primary to everyone, then, and at this point, if I observe that the majority, in fact, did receive the same message from the primary, then I know that the primary didn't lie. Will I get, if the communication is good, will I be getting the same message from everyone? If the primary didn't lie, if the primary did in fact send the same message, will I get 3F+1 messages are identical, or will I get 2F+1 messages? Or what can I guarantee that I will get? How many messages? Assuming the primary didn't lie, assume the network is reliable, didn't drop any messages. How many messages can I guarantee to be matching? 2F+1, 3F+1, what would that be? And again, we have 3F+1 node in the system. Why? Louder. Okay, think about it. Others. Nothing crashed. Network is reliable. How many messages? How many messages can I expect? How many matching messages could I expect to receive? Minimum number of matching. So we're gonna be on the quiz today, so. And why? So that 1F could do what? And then do what? What can they do? It could say they receive a different message, or they could not even send a message. They could not even send a prepared message. They're malicious, or they could send a different one. So what I can guarantee is 2F+1. assuming the primary was honest and assuming the network was reliable, I cannot guarantee that I will receive more than 12 plus 1. Now, I may get 3 of plus 1, but I'm guaranteed to get 12 plus 1 because 12 plus 1 honest replica are there, assuming there was no failure in terms of the network or the primary. Questions? Yes. Louder, so people in the back can hear you too. So what we talked about last time, what? So we talked about, we have, in order to support F failure, we need 3 F plus 1 messages. So to support 1 fault, we need at least 4. To support 2 fault, we need at least 7. To support 5 fault, we need at least 16. And remember what the quorum could look like. Each quorum needs to be 12 plus 1. And for example, I could form a quorum of all the honest one, and then I have F nodes that are bad. And here I have 2F plus 1 that are good. Or that's one possible quorum. Another possible quorum could be that I have F plus 1 good replica and F bad replica. 2F plus 1. And then I could have another set, maybe this partition are not accessible. And these are F good replica. So F good replica are not accessible. Maybe they can't send message or they don't receive message. But I can still form a quorum. These faulty replica, for the time being, could cooperate. Doesn't mean that they always have to behave badly. So I could potentially still form a quorum in which the faulty replica participated. However, if the faulty replica participated in constructing this quorum, it's possible that later on, if you ask them what you voted on, they say we never voted on it. Or they could say we voted on something else. So they could behave maliciously later, but for the initial set, they could, for at any point in time, they could decide to well behave. So maliciousness doesn't mean that they always have to behave badly. Maliciousness, they will any kind of a strategy to try to disrupt the system. And that may entail that at some point or in some, at some point, they, as part of their strategy is that they behave in a correct way, just in order to be able to do something malicious later. So that's a possibility. Question. Does that answer your question? Yes.
So just a confirm the window have a 3F plus 1 replica to ensure that after you prepare state like sending the message, it receive 2F plus 1 message.
And now let's say, why do we need 2F plus 1? Why couldn't have just be worked with 2F? Or right now we say our n is 3F plus 1. Why couldn't we have worked with n equal 2F plus 1? Why do we need this extra redundancy? Why can't we work with the less redundancy? Yeah, the nodes include the primary. We can always assume primary is also sending a prepare message. So primary is just another replica. In fact, you could also optimize the proposed message of the primary is an implied prepared. So if I were to, something happen, there's a sort of a crash. And I need to kind of recover and ask everyone, what did you guys vote on? And anything that bad happens, even if I want to recover system, I always need to form a quorum. I will not make any decision without having the support of the quorum. So when I ask this question, what could happen? What is the one possible core that could be constructed after the core? And let's say maybe a bit of more notation. They transaction A. So this is a quorum for transaction A. And let's say these ones, they got transaction B. Of course, this is not a quorum, just F of them. So what could happen during the recovery? If I later ask what happened in the previous round, what is an example of a possible quorum that is or the worst possible, or what could go wrong? What is the worst thing that could happen if I later ask, what did you guys vote it on?
I think get A or get B, get nothing.
So I could, for example, get these people all say we did B. We got B. So I could have F good replica. I'm not lying. They got B. They said we got B. What could these guys do, these bad replica? They also said they got B. So now I have how many? I need one more. What is that one more gonna come from? One of these good replica need to participate, and that one good replica will say, wait a minute, it was A. And that will ensure that the A, it will ensure that at least we reverse something is wrong. That one replica. If we had done the same example with, let's say, 2F plus 1, if you had done this example with 2F plus 1, then what could have happened, I would have again the same thing, F, A, these are bad guys, and then I would only have one good guy, and then I have F, good replica in dark, who got B. And then if I had to form a core, then what would happen? And my core here now is F plus 1. So I'm going back to the why do we need 2F plus 1? So my form is now F plus 1. What could happen in the recovery? I would have these people would say, same as before. The good guy would have said, no, we got B. And I just need what? One more vote from B. And we have F bad replica. So easily I can get one vote from B. Now this is a quorum for B. This was a quorum for A. So if you only had 2F plus 1, we could have violated it. So that's why we need 3F plus 1. Because at any point in time, F replica would be acting equivocation. So this is why 3F with the 3F would work and why the 2F wouldn't work. An example. So I'll take you a minute to kind of sit on it or think about it, see if you have any questions. But that's an important, yes. No, they're good, but they got something else. You guys are, everybody in that side of the room were good, and I gave you B. And then I gave these guys A, and then we were able to form a core that we succeeded A. And you guys were kind of kept in the dark and you didn't even hear about what they got. All the messages were dropped. You never got it. All you've only heard B, and you have no idea that you all already formed a form for A. So they're good guys, but they kept in dark.
Why don't they get
Adversary. The network could be adversary. Primary is just it's an attack.
Well, we don't consider that only.
It's an attack. So it doesn't, even though you only have F malicious one, but these F malicious one with potentially adversarial network, they could have more impact. They could themselves participate in something, later change their vote, and they could keep essentially F node in dark. They cannot keep more than F node in dark because What happens if they keep more than F node in dark? They won't be able to form a quorum. So if you keep more than F, the maximum you can keep in dark is F, because if you keep more than it, then no side will be sort of a 50-50 split, and neither side have majority, and so, well, nothing will happen. Yes.
This physically, like, yeah, not like forming, because obviously in order to be better.
So you have to see what is the minimum is required. With the crash tolerant, you only need 51% majority. In a sort of a basic fault tolerance for arbitrary behavior, 3F is sufficient. There are models that uses more F, but 3F is the sufficient number. That's an example why 3F, for example, works.
So basically, like, you try by choice or
By choice of the malicious primary and by the choice of the malicious network, not by the choice of the, I don't know, they're in dark. You have no choice. I only communicate with them and I give you a wrong message. You have no choice. But you have no idea what they got. You have no idea you form a form. You just got a message and you're waiting on it. And you may have voted on it too. You might have you got a transaction B and you told everybody you got B. You never heard from anybody else. You voted on B because B looked valid to you, but you don't know everybody else who got A, and everybody else have formed a quorum. You were never informed about it. All the communication to you could be. It's not really a choice. Or your, it's actually the choice of the legislature. Yes.
below example, because actually we have used all the good F, okay, R60, and how do we get another one with replica system?
Oh, you have 12 plus 1. F, and 1. So you have 12 plus 1 more.
The right part, there's one with replica system.
Yeah, so they could be in dark. So we could have this one good replica in dark, so they won't see what's happening. They're no longer accessible. That one good replica who voted for A is not. Now this one is, before these were in dark, now this one could be in dark. So when they form a recovery form, they exclude it. Yes,
Sure. So
sure.
you have to have 3F plus 1 because after those 2F plus 1. Because
We-
that goes to-
Yes, I mean that is a correct statement, but in order to support F fault, F malicious fault, your system has to have a 3F plus 1 core. If you were to support just a crash, not a malicious, then your end would have been this. So protocol that only allow crashes, no malicious behavior, this is the number of redundant copy they need. Protocol that need to deal with malicious behavior, this is the minimum number of replica days. And so that's first part. And then the second part of your question is that you need to form a majority. And you can form a majority with 51%, which would, you can form a majority with 51%. But the problem is, if you just deal with the 51%, F of your system, 1/3 of your system, 1/3 of that majority, at any point, they could change their votes. So that's why we need a 2/3 majority, that even if 1/3 change their vote, you still have another third. And then you can later guarantee that one of those in that one good third will always appear in any future quorum. So with the 3F plus 1, you can ensure that any two possible quorum will always intersect on one honest replica. And that one on this replica ensures that those two forms will have consistency. And this is the worst case of the quorum. Because in the worst case, you could, I mean, you only have F faulty. You could include your F faulty replica and then keep F good replica out. So this is one worst possible. And on the other end, you bring the F faulty and you bring the F1 in dark, but you need one more. And so then you're forced to take one from the good set. And that one will ensure that these two core will not diverge because that one will relay the information. Yes.
How do we know what that is?
The actual value of it?
Yeah, like,
So you have to kind of, there's no, just a kind of, so you kind of suspect, you say, well, expect maybe 20 of our machines will get infected with virus. But it's just an assumption. Okay.
explain, can you explain again why, like, rules can keep it dark?
Keeping it what? Keeping it dark is that primarily send them something else.
In this case, do they consider like the faulty?
No, they don't consider faulty. They just don't, they're not aware of what's happening. They got the wrong message. They're not faulty. Faulty means you intentionally are faulty. In this case means you're doing you're having a malicious behavior. But this is, they didn't do anything wrong. That's the message they got.
So in your case, the primary is.
I'm the primary, I give you I give you a different message compared to everybody else. You're not malicious. I just gave you a wrong message. So, and I could also work with the network to cut the networks in such a way that nobody else can tell you that I've given you some, that I given, for example, her A but I gave you a B. So I kind of collude with the network and then maybe I control the network and you don't even see what everybody else got. You only got B and you say, and you tell everybody you got B. And later on, if they ask you, what did you get? You say, I got B.
So like each replica need to receive at least like 2F plus 1 no message from any other replica to like need to be like prepared.
2F plus 1 is core. So in order to form a core, we need 2F plus 1 message. That's the definition of the majority. The majority here is 2F plus 1.
So like they need to like how many messages?
2F plus 1.
Although like itself is a message.
Hmm?
We consider like the replica itself as some message or
Every replica send a message, so you need messages from 2F plus 1 replica, meaning you got a message from 2F plus 1.
you need like 2 and like you like here
You can count your own vote too.
So at the state of graph of one is two for B and one for A.
This one, this or this?
That's the right one. Could they reach a consensus because like they could not write?
It's not about consensus. Consensus is going through all the phases. This is just asking what happened, for example, before. So this no, because there is disagreement. When you say a majority, I form the quorum of the majority, that means majority agree on something. Not just I got 2F plus 1 messages. These are 2F plus 1 messages that are matching or they agree endorsing the same thing. So I get to the prepared state when I hear from 2F plus 1 other replica that they all got the same message from the primary. I don't get to the prepared state just because I got 2 arbitrary 2F plus 1 messages. So they are the same message. So if I were try to, this is not a valid quorum, or this is, I mean, it's a quorum, but it's not something that immediately you can say, well, B happened or A happened. There is discrepancy. So at least you detect something is something is potentially wrong. So this will allow you to detect something is wrong. Now, whether to decide whether it should be A or B or none, those are different logic. But at least it allows you to detect that there is a potential discrepancy.
So if we find that there are not two as plus one same message, and we can just say the memory.
No, not exactly, not exactly, because primary, I could have been the primary and I send message A to everyone. But then, as we said, the most we can expect to get is 12 plus 1 because F people are faulty and they said, no, I said something else, even though I didn't lie. So as long as you can form your form of a matching form, then you can ensure that at least the primary is not, it didn't lie. But if you see 12 plus 1 messages that one of them is something else or is not matching, you cannot just immediately say, well, primary had lied. The one sending a message could also be lying. Yes.
Which checking there are plus one messages are in
The replica who receives it. So if you are for, you check it for yourself, this one check it for itself, everybody individual. Nobody expects somebody else to do their work. They have to check it themselves.
That is there isn't enough.
So they don't get to the prepare stage. They would only get to this point once they receive enough messages. Otherwise, they stall, and we can talk. We'll later talk about what happened in that case, but they won't get to this state. You would only get to the state if you receive enough messages. Shall we do the quiz now or should we do it on Friday? Okay. All right. So, okay. So what are the questions? So far then kind of coming back to this, what did somebody kind of summarize, what did we achieve at this point? Once I get to the prepared state, what can I conclude? And then I can say that prepared, and what can I say about the primary? Primary at least send some matching messages. Primary didn't lie, let's say. Whether it's good or not, at least for this, didn't lie because I was able to construct a core. So at this point, I know that the majority have received the same messages I have. This one at this point knows the majority have received the same message as it have, and so forth.
So it's like check the form itself.
Again, these are all independent. Independently, I look what I have, and I see I got 12 plus 1 messages, and they're all matching. So I get to prepared. This one looks at the messages received, and it happened to receive 12 plus 1 matching messages. Then this one gets also to prepared. So they're all independent. This is a distributed system. They're not connected. The only connection is that they actually explicitly send a message to one another, but they don't know about each other's state unless they exchange messages. Say that again.
Or when we say the primary is lying, we are actually saying that primary send a different message.
Yeah. So for example, if you collect a set of messages and all of them are different, then you know that the primary is sending is doing something wrong. So now if I were to collect two F plus 1 majority of messages that are matching, how many of them are coming from a non-faulty replica out of those 2f+1 messages? How many of them are non-faulty? I get 2f+1 messages that are matching from 2f+1 replica. How many of those replica are non-faulty? Okay, why? Yeah, so I mean, I don't know, maybe all of them are non-faulty, but I can guarantee that f+1 of them are non-faulty. Because again, coming back to this example, if I get a 2f+1, it's possible that all of them are good replica. But in the worst case, f of them could be from faulty replica. So every time I form a core, I can ensure that f+1 of them are good and up to f could be faulty. So anytime I form a core, I know the majority within that form are always from honest replica or from good replica. Does it make sense? Okay, so now I know that everybody got the same thing. So why do I need yet another phase? Okay, so because the faulty could act normal, so then I would maybe add another phase. But what if the faulty again acting normal and then, I mean, I could always then have another phase, another phase. How do I know they? So that couldn't be it. Because right now, from R4 has observed, and then let's kind of say a more simplistic, R4 has seen everybody got the same message. And also still there's no faulty behavior, at least in this round. R4 sees it got 3f+1 matching messages. And let's say they all were being honest, tell the truth. So in a sense, there's kind of maybe there's a bit of an agreement already reached or a consensus reached because everybody said they got the same thing from the primary. So why do I need yet another exchange of messages, quadratic exchange of message? Okay, that could be the topic for next class. Or actually, we're gonna cover this, I guess, on Monday. On Friday, I'm not gonna say this all the time, but this Friday in advance, you know that you have a quiz first, and then we'll do our tutorial. But future will be more as intended. Surprise. Okay. All right. Thank you.